Hello, I'm Margaret Mooney. I'm with the Office of Space Science Education at the UW-Madison, and you are watching a Get Wise lecture. Today we are fortunate to have Dr. Jeff Morgenthaler with the UW Space Physics Lab, and he'll be speaking on the significance of collisions in the solar system. Jeff?
Thank you, Margaret. Well, we're going to start by looking at what happens in the solar system when we have collisions. First of all, the title of the talk, the informal title of the talk, is When Worlds Collide. We're going to learn about what happens, or after this talk, you'll be able to answer the following questions, which are: do things run into each other in the solar system? Why don't things run into each other more often? Is there evidence of impacts on Earth, on the Moon, or anywhere else? And what's the difference between an asteroid, a meteor, a comet, and a planet? You'll also learn whether or not we're likely to be hit by another planet. I'm going to, in order to introduce these topics, we're going to have to learn a little bit about what the basic structure of the solar system is, and some formation theory on the solar system, as well as a little bit on what the planets are made of. And this is the important part. I'm including a lot of cool websites in this talk so that you'll be able to follow up and you'll be able to plan your curriculum, not just on what I've included in the talk here, which should give you a basic introduction to the topic, but you'll be able to follow the pink links in the website in this presentation in order to take you to relevant websites. So, our first topic is solar system formation. Sun and planets formed from a nebula similar to the Orion Nebula. And here in the presentation you'll see that there is, the Orion Nebula is this bright cloud. If you follow the link, it'll show you a map of where you find the Orion Nebula. It's familiar to all of us. And there are many of these things all around the galaxy. We've got, in the Orion Nebula, or the nebula that originally formed the Sun, you have material left over from the original formation of the universe, called the Big Bang. And you also have material that has been released by stars exploding, or supernova explosions. I affectionately call that recycled star material, or star barf. That material, as you can see here, and does a bit, the material in these nebula, some of it might be denser than others, and material starts falling toward the denser parts of the nebula because of the force of gravity. And in that, as the motion of this material falling toward the center, our self-gravitational collapse happens, not all the material runs right directly to the center. Often the material will miss the center and start running around the other side. So there's this sort of circulation that happens about the center. And in the case of the solar nebula, the densest part of that became the Sun, and because of the effect of gravity and these orbits, the material that's collapsing toward the Sun ends up forming a disk, as you can see on the bottom panel of the slide. This disk, if you look down on top of the disk, you see the view here in this next slide. And as more material starts falling onto this disk, it gets crowded. Things start collapsing, things start running into each other. And particles form called planetesimals. These are things that get progressively larger and larger. They're little planets. That's what planetesimal means. And by gravity, these attract even more material, and they grow and eventually form our modern-day planets. And most of the planetesimals in the solar system got vacuumed up by planets right at the very beginning of the solar system formation, which was about 6 billion years ago. But some planetesimals are still left. And these are the modern-day comets and asteroids, which are called the minor planets. Let's go over the basic structure of the solar system here. In this slide you see we're not quite looking straight down on the solar system, we're looking at an angle. And you see the sun at the center and the planets arrayed out. You should be basically familiar with the order of the planets. The other objects in the solar system, the planets and the minor planets, go around the sun in orbits. Most of the orbits, almost all the orbits, are not quite circular but elliptical. Some are very elliptical, like comet orbits. That's elliptical, sort of egg-shaped or oval-shaped, drawn out. And some orbits are even what's called hyperbolic, where they go by the sun once and then they never come back in a circle, or they never repeat themselves. I want to talk to you about the basic scale in the solar system so that you have an idea of what the likelihood that will be smacked by something is. Here's some pictures of the sun, which is that big yellow thing in the background. You can't see the whole thing because in order to see something like Mercury, which is that little dot off to the far left, you have to blow the sun up to that scale. So basically, the sun is the hugest thing in the solar system. Jupiter's the next largest thing, and so on. And if you remember from the previous slide, this shows the orbits to scale, but you notice that the sun doesn't even show up as an object on that. That's because the sun, compared to the space between the orbits, is very small. So what's the likelihood that one of these objects is just going to accidentally hit one of the others? Well, I think it's pretty small. What would really have to happen is something outside the solar system would have to come in and draw one of the planets off of its orbit and move it in the general direction of another planet, and then maybe the planets could collide. So all of that is a very unlikely sequence of events. So we're pretty much guaranteed not to be hit by another planet. But planets are really big compared to the minor planets, comets and asteroids. And as we'll see in a subsequent slide, there are minor planets floating all over the place because the planets didn't do a good job of vacuuming up every last planetesimal when the solar system formed. So occasionally you'll get a minor planet that gets near a planet. Jupiter is often the planet that does a lot of this perturbing of minor planets. And this minor planet will then go zooming off toward another planet on a collision course. So let's pause here for a minute and summarize what I've gone through so far. Minor planets and asteroids, or the minor planets are asteroids and comets. And they're a remnant of the formation of the solar system. leftover stuff. They orbit around the sun like planets, but they don't always have circular orbits, and their orbits are often much less circular than planetary orbits. Mostly they mind their own business, but sometimes they can be pulled off of their normal orbits by a nearby planet and get flung toward either out of the solar system entirely or toward an unsuspecting planet. So next we're going to talk about what the minor planets are made out of, where they like to hang out, where they generally are found, and finally what happens when a minor planet hits another planet. So you should be able to answer basically the question, what are minor planets made out of? Because minor planets are the basic building blocks of what we are made out of. Remember, in the formation of the solar system, we had this cloud of material that collapsed, and that formed the sun and the planets. And on the way to forming the sun and the planets, it went through this intermediate stage of making these sort of granules or planetesimals. And most of them clumped up into the sun and planets, but there are these extra ones left over. So that's what the minor planets are. They're the leftover building blocks. Some of them are mostly water, ice really, and those form comets. When they get close to the sun, that ice starts to boil off. It's actually called sublimation. They make this pretty tail you see in the sky. There's another Get Wise talk on comets, so I won't go into much more detail. Minor planets that are made from rock and metals are asteroids. The primary metal that you'll find in asteroids is iron. Now, the minor planets are found in a few prescribed places in the solar system where they were not well cleaned out by the planets. One such place is between the orbit of Mars and Jupiter. You'll see in this slide that the orbit of Mars is red, and the orbit of Jupiter is at the very outside and is blue. And between there you have a whole bunch of other orbits indicated. Those are orbits of particular minor planets, which were discovered early on. They have interesting Greek names. Then there's this sort of haze of sort of little dust bunnies looking things. These are the asteroids in the asteroid belt. That's what this place is called. It's between the orbit of Mars and Jupiter, the asteroid belt. And there's a link there that you can follow that talks in more detail about the asteroid belt. Another place where asteroids and comets are found is beyond the orbit of Pluto. And you'll see in the right-hand slide there, a plot of the solar system. Really only the outer planets' orbits show up very well. Pluto's orbit is indicated, and beyond that is this belt of material. Actually, a lot of comets come from this region, and there are a lot of icy type minor planets, and also the rocky minor planets, which are asteroids. And then beyond all of this is a spherical cloud, which is called the Oort cloud, and that is really primordial material that never collapsed into that disk structure that the solar system, that the planets and the sun formed from. And that's much further out. It doesn't show on these scales. And comets like Hale-Bopp and these comets which have thousands of year periods, or that may never come back, that are only seen once. These comets come from the Oort cloud. There's a very interesting website that plots the positions of all of the known minor planets, and you can follow this link in the talk and find that website. So now we get to what happens when a minor planet does hit a planet. Well, what actually happens depends. You can see on the left, if the minor planet is a big planet, if it's a big object, it'll make a big hole in the planet. If it's a relatively small object, which I can click on this. This is a video clip here on the right-hand side of the screen, which shows a movie of an asteroid that came through the atmosphere and was seen over, I guess, eastern Pennsylvania. This is where the movie was filmed. And I guess this computer isn't being very cooperative, but you might be able to see it on your computer. It's an AVI clip. It's a movie of this asteroid burning up in the atmosphere. And it came across eastern Pennsylvania and hit a unsuspecting parked car in New York, as you can see right here on the bottom. So that's not nearly as large an object that made this crater in the desert in the western United States. So it depends exactly what the minor planet is made out of, what kind of impact it's going to make on the planet that it hits. So if something hits Earth, mostly what's going to happen is it's going to burn up in the atmosphere. The atmosphere of this object is attracted by the gravity of the Earth. It starts moving very fast. As it hits the atmosphere, it starts to heat up because of friction, and it starts to burn up. And what we see from the ground when we see things burning up in the atmosphere are shooting stars or meteors. You probably heard of meteor showers, like the Perseids and the Leonids, and these are there are websites that are devoted to observations of these things indicated in the presentation. These are these showers are leftover comet tail debris. So a comet has gone by near the orbit of the Earth and left some junk behind. And as the Earth moves through that, these things come falling into the atmosphere. And because they tend to be very small particles, they burn up in the atmosphere before they get near the ground. But we can see them as they're burning up. And these things, because the comet left debris in a certain place in the orbit of the Earth, these happen periodically as the Earth goes by. And you can see a picture, a time-lapse picture, in the left hand side that shows many shooting stars on one night. They all appear to emanate from one point. That's how a meteor shower tends to look. A picture of that meteor that was breaking up over eastern Pennsylvania is shown in the lower right. If something larger hits the atmosphere, it might make a very large explosion that actually the shock wave of which reaches the ground. And although we're not exactly sure that that's what happened, probably this thing in Siberia called the Tunguska event, which happened in 1908. It was this huge fireball in the sky, witnessed by people in the local towns in Siberia. It knocked down trees for miles around, but there was no impact crater. So the current thinking is that that was a comet that didn't have a rocky or metallic core that would survive the trip through the entire atmosphere to make a hole in the ground. But it was a large enough thing so that it exploded and made a large shock wave which knocked down trees. If a comet hits another planet like Jupiter, which is almost all atmosphere, and incidentally an atmosphere of interesting colors and dynamics and features, you will see, well, this happened in 1994, you may remember, Comet Shoemaker-Levy. It poked holes in Jupiter's atmosphere. And that when objects hit the Earth's atmosphere, it causes fireballs, but they don't quite, we don't have the different layers of gases that are different colors like is on Jupiter, so it doesn't look the same. We have a more interesting surface than Jupiter has, but not a more interesting atmosphere. So when meteors make it all the way to the ground, we call them meteorites. And I like to think that's easy to remember because meteorites, the word is longer than meteors, the word. And so meteorites lasted longer. And there are all kinds of classifications of meteorites, which you may be interested in. There's a website with those listed. Basically, they range from rocky meteorites, stony meteorites, to metallic or iron metallic, rocky iron to iron. Feel free to follow that website. Now, on the Earth, you get these visible impact craters that last a long time, unlike when Comet Shoemaker-Levy came down in Jupiter, it poked holes in the atmosphere, and then the atmosphere sort of swirled around after a few months, and evidence went away. There are some neat pictures on the web of impact craters. These are just a few. Here's an interesting question for you to ponder. Why is it that most of the craters that are shown, the pictures are of desert areas? Why is that? Well, the reason is that there's less erosion. That if you don't have the rain and glaciers or whatever pushing stuff over the crater periodically, it's going to last longer. So here's one in the desert of Australia and another one in the frozen north of Canada. You can see the one in Australia has, it looks like the meteor came in from the left-hand side and sort of lumped up more material on the right-hand side of the crater. There are also effects that happen in the bottom of the crater depending on how large the meteorite is, what kind of material it hit. These are all interesting things that scientists love to study. You probably have heard of the big one. This is the meteorite that was responsible for the extinction of the dinosaurs 65 million years ago. This, it was sort of a big puzzle to put together, figure out exactly all of this, how this happened and when and where it happened. Here are the pieces presented as we know them now. In many places around the Earth, there's this layer of clay. It's shown on the lower right-hand side compared to a quarter. And it's all over the whole Earth, wherever there's sedimentary rock that shows this easily. And it's all about 65 million years old. And there was this mass extinction, so the fossil record is interrupted at about that layer of clay. And so people thought, maybe there was this large event that happened around that. And using surface gravity studies. That's what this sort of funny looking picture on the left is. You can see sort of in blue the outline of this crater looking thing, and then there's another kind of wave that is very suggestive of a crater wall in green at a little further diameter. Now this thing was found off the coast of Mexico on the Yucatan Peninsula, and this is believed to be the impact that was responsible for killing off the dinosaurs. And you can follow these links to learn more about how that worked. Basically, it kicked up billions of tons of material into the atmosphere and altered the climate. And also deposited all this iridium-rich clay around the Earth so we can figure out what happened. Well, the question is, can something like this happen again? What do you think? Various people are trying to answer that question, looking at the probability that something like this happened again. I'll get to this in the next slide. Things like this happened very frequently early in the history of the Earth and the formation of the solar system, but those objects have gone away. But not all of them have gone away, because the solar system formed 6 billion years ago. But 65 million years ago, we had another big hit. So this thing can happen again. But the chances that it'll happen in our lifetime is pretty small. Maybe every 65 million years, but maybe not every 80 years. So I suggest you sleep well at night. About 5 billion years ago, we did have one of these major impacts. At least this is the, we certainly did, because otherwise we wouldn't be a planet. We had to have things hit us in order to get bigger and bigger. All these planetesimals coalesced upon the Earth. But the formation, one of the formation theories of the Moon, which explains a lot of the features of the Moon and their comparison geology, is that something about the size of Mars, which is about half the size of the Earth, half the diameter, hit the Earth about 5 billion years ago, and as you can see in this slide, sort of knocked off a chunk of the Earth, and that sort of sprayed out all over space in this numerical simulation, and then it sort of coalesced into the Moon. And as I say, that explains a lot about moon geology, why its rocks tend to have less iron, because iron sunk to the core of the Earth, and when this thing came by and hit the Earth, only the lighter rocks got sprayed out to form the Moon. Now that the Moon is out there, it provides an interesting record of cratering, because it doesn't have weather. There are no glaciers, there's no rain to wash away or wipe out the craters for the most part. You can see these close-up pictures of the Moon. There are these things called maria. The maria are areas that have been filled in by lava flows, and you can see many of them are circular shaped, suggesting that a large meteor hit that part of the Moon. The crust broke, lava spread out and filled in whatever was there, and then subsequent craters have formed on that. And then there are parts of the Moon that never had lava flows on them and are very cratered. It's shown on the right-hand panel. You can also see, because there is a little bit of weathering on the Moon from the solar wind, and also from the impact of other craters, or the effect of other craters, you can see that there's sort of an older crater that looks like it has some very new craters in the middle of it, and then some sort of medium-aged craters on the edges. And there are, you can see in the middle of one of those craters, there's a little bump. That's a feature that happens in many craters in a soft material, that you have this sort of central raised peak as the material rebounds from the impact. So you can actually estimate the age and what's called the cratering rate from looking at the impacts on impacts in the moon. And some poor graduate student was sent to work counting all the craters and craters within craters to figure all this out. Other planets in the solar system have craters. Mercury looks very much like the surface of the moon. And here, very clearly, are shown these little central peaks in the middle of the craters. Mars, also on the right-hand panel, has craters all over the place. Although Mars has had some, there's some wind on Mars, because it has a very thin atmosphere right now. At one time there was water. This also shows some evidence of stream flow around these craters. Two large moons of Jupiter and several moons of Saturn show evidence of cratering. You see on the left Ganymede and on the right Callisto. These bodies look a little bit different than the moon. They're primarily, the surfaces are ice, so when something hits them, it reacts a little bit differently than sort of a dusty, rocky surface like the moon or Mercury. And finally, asteroids hit each other. Asteroids become meteorites of each other, however you want to phrase that. And so you can see little craters on some of the larger asteroids that we have good pictures of, and even some craters inside craters there. So, here we are with some answers to our questions that we started at the beginning. Why does stuff hit us from outer space? Well, there's stuff left over from the formation of the solar system floating around. And that stuff called minor planets, which are asteroids and comets. The scheme is you have some minor motion in the orbits of the minor planets that might bring them closer to a planet such as Jupiter. That perturbs the orbit. Maybe the next time around it gets perturbed some more, and then that starts to send the minor planet off towards another planet. And that's how that minor planet can become a meteor or a meteorite. Where do we see impact craters? Well, probably pretty much anywhere where they haven't been erased. And what role do impacts play in the evolution of life on the Earth? We know they killed off the dinosaurs, hoping they won't do too much more, but there probably will be, there definitely will be another big impact at some point in the future history of the Earth. I'd like to acknowledge the source material of this talk. Most of it's taken from the textbook Universe, which I used for an introductory class on the solar system here at UW that I taught in the spring of 2000. The web link at the very beginning of the slide of the presentation to my homepage will give you the lecture notes of that, or direct you to the lecture notes of the Astronomy 104 course, and that material is from the Universe textbook. There is also a very interesting project in tracking asteroids. It's part of the K through Infinity program that's sponsored here at the UW. Follow that website. And there is, among many other things on the web, a fun crater making activity that you can find at the last website. I hesitate to suggest it too highly because it involves flour and paprika in the classroom, which could get a little messy. Thanks for your time.
Thank you, Dr. Morgenthaler. I don't have a question on collisions per se. I learned a lot. But I'm still intrigued with, how do we know that the Oort cloud is primordial? How do we know? How have we tested that?
Well, we've been able to get some idea of the motions of material in the Oort cloud, and we see that it's actually it is difficult to detect these things because they're very far away, but we have detected several of them, and they appear to be moving in the way you'd expect if they're distributed spherically around us. And also from comets that come in, like Hale-Bopp, Comet Hyakutake, things with very long periods. These seem to come in from random directions, not always right in the plane of the solar system. And in particular from comets, we can see when they start to melt off their outer layers of water, they take with them other stuff, and we look at the composition of that other stuff. And it looks similar to the composition of material out in what's called the interstellar medium. It's the material that's between the stars. That material between the stars, the interstellar medium, is what we formed from. It was a very dense part of the interstellar medium, one of these nebula that collapsed to form the sun and the planets. But it was the interstellar medium nonetheless. So if we see a commonality between the composition of comets that are coming from the Oort cloud and material in the interstellar medium, which we can look at as we see starlight filtering through it, that's how we deduce that the Oort cloud is really this leftover interstellar material that partially coalesced.
Thank you.
There was a news item recently that suggested that most of the water in the oceans may have from comets.
Well, most of the water on any planet, I mean, since we know we have water here, we're not sure we have water on other planets per se, although we do have some on Mars. Because the planetesimals were the building blocks of the solar system, and icy planetesimals have become modern-day comets, it stands to reason that the water came from those icy planetesimals. They didn't come from the rocky planetesimals because those are rock. So not only does the water from the oceans come from comets in that form, but also many interesting long-chain carbon-containing molecules that are necessary for the formation of life have been observed in comets by the same mechanisms that we look at material in the interstellar medium, draw that parallel. So we look at material in comets, and we see, hey, these are the building blocks of life coming from comets.
So is it fair to say then that we wouldn't be here if it weren't for impacts?
Definitely the in more than one way, the impacts not only formed the Earth itself and the planets and the sun, but the composition, the specific composition of each planet is determined by what hit it. For instance, out at Jupiter, there was a lot of just plain old hydrogen gas hanging around. And that got sucked up by Jupiter, which is why Jupiter is mostly hydrogen and helium. Whereas in the inner solar system, where the sun was bright, it ionized the hydrogen and made it more difficult for that hydrogen to be attracted to and gravitationally bound to the inner planets. They were hotter. Things like that made it so the inner planets were primarily rocky. And because inner planets at some point, particularly Venus, Earth, and Mars had dense atmospheres that allowed some comets, or some planetesimals, like comets, to come in and have their gases actually trapped rather than hitting the surface and that material going back away. Answer your question?
Yeah, pretty much. Thanks. I guess one other question, or a couple. One is, are the same kind of impact processes occurring around other stars or planetary systems around other stars that have been found? And my second question was, there was a cartoon in the New York Times last Sunday that talked about possibly going to Venus to find oil.
Well, what was the second?
Oil. Did oil come from space?
Did oil come from space?
Gasoline, crude oil.
Huh. Okay. Well, let's see. To answer your first question, we have recently detected planets around other stars, proving there are other solar systems, and we have detected these disk-like structures around other stars, which confirms our ideas of how the solar system is formed out of this. What started out probably as a circular or spherical cloud collapsing into a disk, and then planets forming in that disk. The planets around other stars, we know the disks around other stars. So all these processes which we think form our solar system seem to be forming other solar systems. And so impacts, comets, all these things stand to reason to be happening in these other places. As far as oil coming from impacts, that seems, well, the standard theory for where oil comes from is that it's actually biological material that has been buried underneath sedimentary deposits, like on the bottom of an ocean. So if you have an ocean teeming with life, with rivers dumping material in, life dies and falls down to the bottom of the ocean. You have sediments covering that, and then over many millions of years, that sediment layer builds up, squashes the organic material down, and that gets compressed to form the petroleum products, natural gas, oil, things like that. That's a standard picture. I don't know of any oil-containing comets or meteors, but the connection, you can probably see that if there was some mass extinction, well, life's going to die anyway. I really don't. I don't see the connection that an impact would be directly responsible for oil deposits.
A few years ago, an astronomer from Cornell University, Gold, had talked about this connection, and I believe there was a crater in Sweden where they were going to try to drill about 8 or 9 kilometers deep to prove this theory. Now, I don't know what happened to the drilling expedition. I don't think they got further than maybe 4 or 5 kilometers, but they were expecting to go down to about 8 or 9 kilometers to prove it. And related to that was my question, that if you find all the other organics, I mean, you found alcohol, you found other organics, why couldn't you have other heavier or longer chains that basically forms the crude oil? I mean, what's there to prevent oil from occurring in space?
I guess that's an excellent point, and I'm thinking of the quantities that you'd be interested in for the oil industry, for instance, where you have it's just millions and millions of cubic meters of material, and if an impact were to deposit that much material, it would probably destroy the Earth too. I mean, you would get. It's possible that these materials are contained in moderate quantities in minor planets. I don't know if it would be a good business decision to go looking for it. It'd be an interesting scientific discovery.
If you could form oceans from comets, and certainly Earth is mostly covered with water, around 75%. And presumably we don't have the same amount of oil in terms of volume on the Earth. Why is it not conceivable that perhaps some organics came from comets? I mean, I don't see the distinction between water and organic compounds.
The water has an additional advantage that is part of a cycle that the environment, the biomass, participates in. And so where you have, if you have some water, enough water to form life, and then that life makes an oxygen-rich atmosphere, which then shields the water from being broken up by ultraviolet radiation from the sun, then that allows more water to accumulate. Water comes from other chemical processes. You can get and cycle through water easier than oil. There aren't clouds of oil in the atmosphere that are raining down petroleum, maybe on Titan, Saturn's moon, but not in Earth. And so if there were, and maybe very deep, there are, because in the early formation of the Earth, you had a process called differentiation, where the whole Earth, just 6 billion years ago, just after these planetesimals were hitting the Earth, everything was very hot because it was continually being impacted and heated. The heavier materials sunk to the center of the Earth by gravity. That's why we have an iron core in the center of the Earth. It could be that out further there are different materials with different densities. In fact, we know that we have lots of silicates in the crust of the Earth, and these were the lightest kinds of the lightest material, other than the atmosphere, of course, and so that sort of floated to the top, and it's still warm enough in the middle of the Earth to actually have a significant amount of molten material. I'd expect, though, this differentiation process and the temperature change might make it difficult for certain hydrocarbons to exist in, you get them too hot and they break down. So even if there were some sort of oil reserves in minor planets, I'm not sure if it'd be easy to find where that ended up on the Earth, if we haven't found it already. Maybe 8 miles down there is.
Thank you very much. Thank you for a very entertaining talk.